Hey folks, sorry about the lateness of the video. I got lost in track in time just today and also last night a little bit. Um, day three notes for you. I know it says day four, day's run. Sorry, I'm just rolling with it right now. Today I'm going to talk you through weight and mass, free body diagrams, run a problem with you, Newton's third law, and also Newton's second law. All right. Um, for my hybrid A kids and my distance learners on Monday, you'll see the quiz that follows here. We're going to talk about inertia. Basically, object at rest stays at rest, object in motion stays in motion. Um, we're going to talk about universal gravitation concepts. That's the equation where we had in the top right of the PowerPoint, where we saw F of grav equals G m1 m2 over d squared, basically talking about how mass plays a role in that, meaning that the larger the mass, the larger force of gravity on it, the smaller the mass, the smaller force of gravity on it. You're going to see a Newton's second law, Fun equals Dema. Kinematics, that's basically those first couple equations that we've talked about. A equals VF minus VI over T. VF squared equals VI squared plus 2A delta D. Delta D equals VIT plus 2 or plus 1 half AT squared. All right, using something like that. And then graphs involving dropping and throwing upwards. So you'll see a D versus T graph. You'll possibly see a D versus T of dropping, V versus T of dropping, D versus T of throwing, V versus T of throwing upwards. Okay. Um, for us, for hybrid B and distance learners on Monday, you'll get days. You'll get a lab there also as well. Tomorrow for you folks, you'll see it's kind of homework time just for you to get through stuff and work through stuff. Okay, so here we go. All right, mass and weight. Mass is the amount of matter in an object. When we look at the concept of mass, um, it is really as simple as how much solid, how much liquid, how much gas, the three states of matter that we make up. You could also think of it as the chemical bits, the elements, the compounds, the molecules, the ions, all of that different stuff that is what makes us. That's what mass really is for us. As Americans, we don't do a great job of this. Usually we look at it and say, all right, our mass is in pounds. I want to say, I think an old world or an old school one is slugs for mass, but I could be wrong. I can't remember what the old one is for us. Mass in the metric world is like kilograms. Um, so if I were to look at myself right now, I weigh about probably 115, 120 kilograms. All right. Weight is the force of pull of gravity on an object, meaning that that's an actual legitimate force. So when you go to the doctor's office and you stand on a scale, what it's measuring is the force of the pull of gravity there. All right. On homework, I mistakenly put weight as W. I probably should have put force of gravity there as well. All right. Another little variation of the formula, F of gravity equals mg, mass times gravity. All right. So we ask a weird question. Will your weight be the same on the moon? Now, for a lot of people, when we think about the moon, we think about it has, you know, not as much gravity as the Earth. Well, that's 100% true. It does have gravity because it does have mass. It's just that because it's a sixth the size of Earth, the gravitational pull there is about 6 times less. So if on Earth I weighed roughly, let's say, 1,000 pounds or 1,000 newtons, on the moon I would weigh 6 times less than that. All right. So what's that? 10/6. So that's what, 5/3. All right. So basically 170 something newtons, right? Um, Again, our mass there though going to be the same. And that's the nice thing is that the amount of matter that we have isn't really going to change too much. All right. What about in space? What would we weigh there? So if you said, you know what, I'm done with all this stuff. I'm going to go steal a SpaceX rocket from Cape Canaveral. Not that you can do that, or not that I'm encouraging you to do that, by the way. But you're going to get a SpaceX rocket. You're just going to go off into outer space and just chill out there until everything kind of blows over, so to speak. Now, your weight there should be basically zero. The hard part about it is that force of gravity, according to the universal gravitation constant, is always going to shrink. Meaning, no matter how far away from something we get, it's going to be like an asymptote in math. Meaning, it approaches zero, but it doesn't actually touch zero. All right. That weightlessness feeling you can actually kind of simulate here on Earth. You can be apparently weightless, is what it's called. Um, there's a airplane that NASA operates to train their astronauts and also sometimes private citizens that goes up really fast and then it drops really fast and it goes up and down, and it just does like this snake-like fashion. As it's going down, it actually accelerates at the rate of gravity. So what happens is it's going fast enough where the people inside of it actually feel this weightless concept. Now, you probably felt it before as well. That little hitch in your stomach where all of a sudden it pops up. Probably the easiest place is on Ipava. If you're driving by Century and you're going, it's a speed limit or faster than the speed limit through the 185th Street intersection. As you drive on Ipava and you hit that, you get that little bump. So what happens is when you jump up, you're actually feeling that kind of weightlessness, so to speak. Kind of an eerie, weird feeling for us, right? All right, so grab a calculator, try this one out. A certain science teacher once had a mass of 84 kilograms. How much would the science teacher weigh on Earth and on the moon, with g equal to negative 1.6 meters per second per second? Now, on Earth, the gravitational pull is going to be negative 9.8, all right? So what we're going to do is we're going to use the formula that you saw on the previous screen. We're going to use F of grav equals mg, which looks an awful lot like Newton's second law, right? The only difference is that we're going to have a specific gravity, like we do here on Earth, of 9.8, and that's going to be kind of representative of where we are in the world, so to speak. Meaning, if you go to like Mount Everest and you go to the top of Mount Everest, that 9.8 changes. If I remember right, I think it's like 9.7 or 9.6. If you go to Death Valley, instead of being 9.81, it's like 9.85. So it doesn't change a huge amount. So if you're looking at it and saying, well, if I go down to my basement, I feel such a greater gravitational pull. That's more mental than it is actual reality of it. All right. So with this one, what we see is we take 84 times negative 9.8 and we get negative 823. The negative just means for us this force is being applied down. When you look at that scale, that's what it's measuring, is how much force is gravity pulling down on us with. All right. On the moon, 84 times negative 1.6. Again, that's the moon's gravitational pull. It would be negative 134.4. Now, weird thing is if we were to go to Jupiter, Jupiter, because it's such a large planet, is actually going to be 6 times more. So what we would see is that 823, it would actually be closer to about 5,000 newtons. So if you think, right, I weigh 120 pounds here on Earth. All right, perfect. On the moon, you'd weigh 720 pounds. Me being 240, I'd weigh about 1,200, 1,300 pounds on the moon, which is absolutely maniacal to think about, right? Because that's just so stinking heavy. But again, the size of Jupiter is going to be so much bigger than us. All right. So onward, free body diagrams. Free body diagrams are really interesting for us because what they do is they start to talk about what is actually working, what are actual forces, what is actually happening with these objects. All right. The first question we ask is, do forces have a magnitude? Now, magnitude is a big fancy word that it's taken me a bit to really get a grasp of. When I first started teaching physics, I didn't necessarily understand why we talked about magnitude. But magnitude on the previous slide was, what's the magnitude of the weight on the moon? It was like 134, right? What is the magnitude of the weight on Earth? It was 832. Magnitude is a big fancy term for what's the number? What's the value? What's the numeric quantity? All right. What is the magnitude of your shoe size? Well, I wear size 12, so the magnitude would be a size 12. All right. Do forces have a direction? This one's really weird because when we think about it, if I want to push a desk across a room, or if I want to push a chair across a room, do I have to have a specific force in a specific direction? Well, yeah, right? When we think about the most basic force that we've ever been around, which is gravity, gravity is always pulling in one specific direction, down towards the center of the earth, right? Now, imagine if all of a sudden you had some sort of room in your house that had an anti-gravity device on, where the gravity was on the ceiling as opposed to the ground, right? The first time you entered that, you would crash into the top of the ceiling. It hurt, right? But after that, you could do some seriously sweet like flips and cartwheels and stuff like that. So when we ask, does force have a direction? 100% it does. So the combination of these two means that forces can be classified as a vector. Now, please don't get ahead of ourselves here. when we think about a term of a vector, math class uses these pretty hard. Like they talk about the angle of the vector. They talk about the magnitude of the vector, like the size of the vector. I remember in engineering courses in college, we had to have the protractor out to try and get the exact angle that we needed for the vector. It was all kind of crazy and kind of tricky. All right. So the beautiful thing is we don't have to worry about that. All right. Um, so students sitting in their desk, what would the free body diagram be for that student? All right, so we look at this student here sitting in the desk, all right, old Calvin and Hobbes photo, right? One of the basic forces that we have that we're always going to have present here on Earth is that force of gravity, and gravity is working downwards, all right? So then we ask the question, is the student falling? Meaning, is the student accelerating towards the Earth? Is the student accelerating towards the ceiling? Well, none of those answers are true. The student is just sitting there. So that means there has to be a force that balances this out. Well, what's going to balance out this student at this time? Well, the thing that's going to balance out the student is the desk that they're sitting on. So remember, in order to have an unbalanced equation or an unbalanced force, we have to have acceleration. This student is not experiencing that. Because they're not experiencing that, these forces would be balanced. If you looked at the magnitude, size of the arrows, they're going to be the same. If you look at the direction of them, they're going to both be opposite so that they cancel out. All right. When we look at this then, this gives us the direction of Newton's third law, right? Throughout the course of the day, once I got to the slide, all I had to do was recite for every action there is, and most of my classes took over. You've been conditioned very, very well by your middle school science teachers. Yes, you are right. For every action, there is an equal and opposite reaction. Now, when looking at that concept, when looking at a reaction, what does that even mean to us? Well, it means that forces need something to push against. All right? So if we look at a couple pictures here, left one from the Matrix movie, fictional, I get it, right? But what we see is the action force is the gentleman's pushing down on the hood of the car. All right? The reaction is the hood of the car is pushing back up against the gentleman. All right? As we look at that, what we see is the downward force is larger. It's an unbalanced force because that vehicle is starting to brake. Okay? We look at the right picture. All right? We got the bat hitting the ball or bat pushing on the ball that way, right? We got the ball pushing on the bat back that way. The force that should be bigger is the bat pushing on the ball because we know that the baseball is going to fly. Now, if we change this up and said, you know what, 8-ounce baseball, that's not how you should play baseball. We should take a 10-pound can or a 10-pound bowling ball, shoot it that way, right? Now, if you hit that with the bat, guess what's going to happen? The bowling ball is going to win. If that bowling ball is going at 80 to 90 miles an hour towards the batter or towards the plate there in baseball, well, that thing's going to win. It's going to have way more force because of the higher mass. All right? That bat is going to not do well there. Okay? So, check this out. I didn't honestly know until about a year or two ago that there were trampoline like world championships. So, if you look at this, and granted, these things are a little bit more scaled up than our backyard trampoline. But what we see here is the trampoline person is pushing down on the trampoline. That's the action. The reaction, the trampoline pushing back up. In this case here, what we see is the force that's stronger is the upward force. It's going to push that guy back up in the air, or that gal back up in the air, right? Now, what if the guy's force was stronger, the gal's force, or the trampolinist's force was stronger? If that force was stronger, what's going to happen is they're going to punch a hole in that trampoline. If they're balanced, they're going to hit and just stop. All right. You could talk about a recoil of a gun as an action reaction force, right? So here's what I want you to do. All right. Take a look at this. This is a little bit more complex of a problem for us. The reason that this one is so tricky is because as you look through it, we see that there's a force of 6,255 newtons initially. We then read the second paragraph when we say that the speedboat travels through the water. It experiences 3,725 newtons of resistance. All right, that's another force. If the 1,250 kilogram boat mass traveling at 4.5 meters per second, that's a velocity, when it opens up the throttle, how fast will it be traveling after 2.5 seconds? Time. Folks, there's a ton of information here. I mean, we got 5 different numbers, 2 of which are forces. We got a mass, we got a velocity, we got a time, and now they're asking for how fast. This one was super intimidating the first time I looked at it. But with the prompts, I hope it becomes a little bit better for us. We want to find the unbalanced force, right? So that's our first part. So unbalanced force, usually what we do with an unbalanced force is we say, okay, Fun equals ma. All right, well, if we're looking for Fun equals ma, we know here, let me highlight some stuff, sorry. Let me get my mouse going here. Pen, I want it to be a different colored font. Right, there's our mass. All right. The incorrect way that people go about this is they say, okay, Fun equals ma. I got a mass of 1,250 kilograms. My acceleration, there isn't one listed, so let's use gravity, 9.8 or negative 9.8. Here's the hard part. This speedboat then, if we're talking about gravity, this speedboat is going downwards, meaning that you are operating speedboats on waterfalls. It's not a good, I don't think, according to the operation or operator's manual, that's the way we use it. So that mass is not something that we can use. So what we instead have to do is think of, okay, unbalanced force, that could be a net force. Well, if we see that the engine is operating at 6,255 newtons, the resistance of the water is 3,725, now the question becomes the unbalanced force. Are those two acting in the same direction? Meaning when the boat's going that way, is the water helping it to push that way? No, that's not how it works. Again, this term of resistance means that it's fighting it, it's going against it, it's opposing it. So when we look at our unbalanced force, the force of our engine minus the force of the resistance is how we're going to find that unbalanced force. The boat's going to try and go forward. The water is going to say, I don't want to part for you, I don't want to move for you, so I'm not going to. Well, after a while, what happens is the engine develops enough force that it's able to actually go through the water, right? How much force extra does it have? 2,530 newtons of force, all right? Now, big question that was asked today, and it was an absolutely fabulous question. What happens if those two numbers are the same? What happens if the resistance is exactly the same as the engine? Well, what'll take place is nothing. That'll be a balanced force. Everything will cancel itself out. We don't then get any movement, any acceleration, anything there. All right. But in this case, we actually do get some unbalanced force. All right. Second part then, it says, what's the average acceleration? Now, usually when we get to a point like this, we want to use that previous answer from before. Now, we could look at it and say, well, I have a mass, I have a velocity, and I have a time. The hard part is that when you start looking at kinematic equations, we don't have necessarily a final velocity. We just know a 4.5 when we open it up. That's our initial. All right. If we look at the VF squared equation, well, we don't have a final velocity and we sure as don't have a distance, right? If we look at the delta D equation, well, we don't know the distance yet again either, right? So having multiple variables that are unknowns in our equations, we can't solve for that. So what we have to do then is say, okay, the only equation we can use is Fun equals ma. So we take our force of 2530 from the previous equation, we take our mass, and we start plugging those in. All right, so we take that 2530, we divide it by 1250 kilograms, and what we end up seeing is our acceleration in this case is about 2.02 meters per second squared. All right, so now we know how fast this thing's accelerating, meaning that after a second, it should have gained 2.02 miles per hour. After 5 seconds, it should be 10.1 meters per second of an increase in speed, so to speak, right? So we see it took 2.5 seconds. So now we want to know, hey, what's the final velocity? All right, well, we know the acceleration from the previous problem. Now, please, something to be aware of. If we mess up that acceleration in the previous problem, I'm not going to use that against you in this problem. Yes, you will lose point in part 2. You'll lose some points there. Yes, you will. But in part 3, whatever your value is, I'm going to keep that separate as a complete and new problem for us. All right, VI is 4.5 meters per second. My time is 2.5 seconds. To find my final velocity. Well, to find final velocity, I can use A equals VF minus VI over T. I could use VF squared. I can't use delta D, and I can't use Fun equals ma, right? So then, because I see I have a VI, well, that still doesn't do anything. I have A equals, and I have the VF squared equals. Because I have a time, that immediately tells me I can't use the VF squared equation. The VF squared equation has a distance. I don't know that yet. So I have to use A equals VF minus VI over T, right? Again, that's a quick and easier way to kind of go through those equations and say, this one's the best one for me. So I plug this stuff in. Folks, this is a tough solve. This is probably one of the more challenging, more difficult solves that we're going to have to try and find VF here. All right. First things first, we got to get the 2.5 off of the bottom of that fraction. So I'm going to multiply both sides by those two. All right. Once I do that, that leaves me with VF minus 4.5. Now, I'm going to punch that into my calculator. And if I remember right, from running this today, I think it's like 5.5 or 5.05 or something like that. All right, equals this. So what we see here is that is the sum from these two, right? Then all I did to get VF by itself was just add 4.5 to each side. Once I did that, that's how much my change in velocity happened over that course of time. If I started at 4.5 here, that means that my final velocity here should be 9.55 meters per second. All right. Again, we started out by asking, hey, what's the amount of unbalanced force? Use that unbalanced force to calculate acceleration. Use the acceleration to calculate the final velocity. Now, you'll get all three of those prompts as we go through it. I'm not going to ask you to solve this just straight up like it was at the beginning. Okay? So, here's what I want you to do. Third law, really nice little bit here about the third law, but I'm not going to waste your time with that. Put the video on pause. Try this problem out, where we see a 150,000 kilogram rocket traveling in outer space at 975 meters per second, fires its engine, speeds up to 1125 in exactly 1.25 minutes. What's the acceleration? What force is exerted? All right, so put it on pause, try to run these, see if you can get them. Okay? All right, hopefully you paused it, hopefully you tried it out. So all I'm doing in this slide is just putting the numbers into places. My mass is 150,000. My initial velocity is 975. My final velocity is 1,125. My time, this is the tricky part. If it's a minute, if it's 1.25 minutes, 1 minute is 60 seconds. I can't have time in minutes. I have to have it in seconds because that's what my velocity is on. So 1 minute is 60 seconds. A quarter of a minute, 1/4 of 60 is 15 seconds. Those two together, that's where I got the 75 seconds from, right? This one here, asking for A. So if I look at it, I see a mass. The mass is kind of a tease as far as numbers are concerned for us. We would need a force in order to calculate an acceleration using that, which we don't have. So then we start looking at the equations. Is it our A equals? Is it our VF equals? Is it our delta D equals? Well, if we have an initial velocity, that leaves all three still open. If we have a final velocity, delta D goes bye-bye. So now I'm just looking at, is it VF squared or is it the A equals? This one, because it has a time, it's going to be the A equals. Again, VF squared equation needs a distance. We don't have distance. I can't force that time into a distance and say, you know what, I went out for a walk today. I walked a total distance of 75 seconds. No, that's a time. It doesn't work that way. Okay? So we use this equation. A little easier solved than the last one. We put 1125 minus 975, punch it in your calculator. You're going to see that's 150. Over 75, 150 divided by 75, we find our acceleration here is 2 meters per second squared. All right. Now that we know the acceleration, we can move on to part B. Part B says, what is the unbalanced force? All right. Well, if I know the unbalanced force, or if I want to find the unbalanced force, I have to use fun equal to ma, right? Mass, just used it there. That's 150,000. The A I just calculated again. So those are my two numbers that I'm going to use. I'm going to take 150,000 kilograms times 2 seconds. All right. My force here should be about 300,000 newtons. Again, we measure force in newtons. Masses are measured in kilograms. Accelerations measured in meters per second squared. All right. So tomorrow, what I'm going to want you to do, take a look at homework. I think I got answer keys up on Schoology. Check that stuff out. If you got questions with that, shoot me an email. Monday, expect to be taking that quiz, all right, and also working through the lab, which I'll share which I believe is already online for us if you want to start that tomorrow as well, okay? Otherwise, again, sorry about the lateness of the video. I wish I would have had it up there this morning for you so you could have used your time better, but unfortunately, life got in the way of that. So, all right, take care, folks. If I don't talk to you, have an absolutely fabulous weekend. We'll talk to you Monday for sure, all right? See you later. See ya.